Buoyancy is a force that is going to be an interaction between a fluid and an object displacing that fluid. For example, I'm just going to put a circle in a fluid. So it's not sinking into the fluid, it's sitting out of the fluid just a little bit, displacing some of that fluid. If my object is stationary, what would be my free-body diagram? So we're going to have an object with a force Fg pointing down, and we're also going to have, if it's in the water, we're going to have our new force called buoyancy force. Fb in this situation, the force due to buoyancy. So if our object is remaining stationary, it means that the sum of the forces is going to be equal to 0. One of them is pointing in the upwards direction and the other one is pointing in the downwards direction. So that means that we get our Fb minus our force due to gravity. So if we look at this object, it's going to be floating. So that means our force of buoyancy is going to be equal to the force due to gravity. Force due to gravity is equal to mass times gravity. This is kind of everything that we've done previously in this regard. We've looked at the idea that balancing forces, what are those forces going to be? But we've kind of got an odd situation now, don't we? Because this is saying the mass of the object, right? But we want to relate this to the fluid. So if we look at the volume of which the fluid has displaced, right? So if we look at this area here, this is where the water would normally be, but the object has pushed it out of the way. So the mass that is being displaced here would be the same as the mass of the object, right? Because it's pushing out a certain amount. It can't push out more than what it actually would weigh, because then if it's pushing out more water than what it would weigh, the force it applies down is going to be greater than the force that it applies up. So our forces must be balanced here. So the mass of the fluid displaced is going to be equal to the mass of the object. I'm fairly happy with that, but mass of the fluid though. We could figure out what the mass of the fluid is. We could take the same volume of it, but there's something else that we know about a lot of things, and that's called density. So density has the symbol of a rho, sort of a curly P. And this is our mass divided by our volume. Everything has a density. You have a density, the air has a density, water has a density as well. The density, we can now rearrange and solve it for mass. So this means that we can get the density of our fluid is equal to the mass of our fluid divided by the volume of the fluid. If we substitute that back up into our mg, we would get rho v G. We have the density of the fluid, the volume of displaced fluid, and G is our gravity. This means when you put like a boat into some water, it is going to push that water away from itself. But we want to cause a larger displacement in the water. That's why boats have quite a large hull. It pushes the water out of the way, allowing its mass to displace a large amount of water and thus causing it to float. Because the forces then, it's displaced the same amount of mass that it has got, thus allowing it to balance its forces in the vertical direction. Here's a question for you. Let's draw it out. You've got a tub like this, and I put an object down the bottom such that it is experiencing a normal force. Which way is the buoyancy force acting? Even if there is a normal force, i.e. you've got for this object down here, you would have a normal force, Fn, you would have a Fg pointing down. Think about where the water has an option to go. Only place the fluid can go is into that space there. It can't go anywhere else inside of this box, so therefore the object must experience a buoyancy force, Fb, going up. My buoyancy force would be something like that, so it would be very, very small. But buoyancy is still going to try and cause it to rise. If there's no questions for me, then there are questions for you.